All right, hello. So this is video number 2 of section 7.1. And like I mentioned, this will actually be the last video of this section. So at the end of last section, right, or at the end of last video, excuse me, I had written theorem 2 on the board, which said that a matrix is orthogonally diagonalizable if and only if it is symmetric. So there was one case of that theorem that I had said we hadn't looked at yet, right? Because what we showed in theorem 1 was that any two eigenvectors corresponding to distinct eigenvalues of a symmetric matrix must be orthogonal. And so the case that we had sort of left out was a case like I have on the board, where I have an n by n matrix with fewer than n distinct eigenvalues. And so the natural question to ask to sort of study whether or not theorem 2 is completely correct is what happens if I have less than n eigenvalues, that is 7, -2. Specifically, will the eigenspaces corresponding to an eigenvalue of maybe multiplicity 2 always contain at least the number of eigenvectors corresponding to the multiplicity? There's a natural question to ask, is this matrix even diagonalizable, let alone orthogonally diagonalizable? So with this example, I want to basically show you yes, that this matrix and all symmetric matrices will be diagonalizable. And then I want to sort of demonstrate how we can actually orthogonally diagonalize this matrix, even though it doesn't have n distinct eigenvalues. So I've already stated here the eigenvalues of this matrix are 7 and -2. So what we want to do first is calculate the eigenvectors for lambda 1 equals 7. And so to do this, we want to row reduce the matrix A minus 7i, which is equal to -4, -2, 4, -2, -1, 2, 4, 2, -4. Let me make sure I've got everything there correct. Yeah, that looks good. All right, so this row reduces to, so we'll say we row reduced the following matrix: 1, 1/2, -1, 0, 0, 0, 0, 0, 0. And so looking at the corresponding homogeneous system of equations, we have exactly one equation with two free variables, x2 and x3. And so solving for our one non-free variable x1, we get that x1 is equal to -1/2 x2 plus x3. And so this means that the parametric vector form corresponding to this homogeneous system is -1, 1, -1/2, 1, 0 times s plus 1, 0, 1 times t is equal to 0, where s and t are both real numbers. And remember, for every free variable in this homogeneous system, we should have at least one, well, exactly one vector corresponding to that free variable. So this vector corresponds to x2, this vector corresponds to x3. And remember, while every single linear combination of these two vectors is an eigenvector of A, it's probably easiest just to take the smallest scalar multiples of these two vectors that don't involve fractions, and let those be the eigenvectors we choose. So here, v1 and v2 are both eigenvectors of A. corresponding to lambda 1 equals 7. Notice they're linearly independent, and both are eigenvectors for lambda 1 equals 7. So we're not quite done. We need to find the eigenvector for -2. And so we're going to do that in the same way. By row reducing matrix A minus -2 times I, which is equal to the matrix where I add 2 to each of the diagonal entries of A. And this row reduces to the following matrix: 1, 0, 1, 0, this is a little more distinct, 0, 1, 1/2, 0, 0, 0. So this gives me the homogeneous system x1 plus x3 is equal to 0, x2 plus 1/2, x3 is equal to 0. Solving for my two non-free variables now, x1 and x2, I get negative x3, negative 1/2 x3. And so the parametric vector form would be -1, negative 1/2, 1. And again, I want to take any scalar multiple of this vector to be my eigenvector. So we'll say that one eigenvector for lambda 2 is equal to -2 would be -2, -1, 2. And this corresponds to the eigenvalue lambda 2 is equal to -2. So notice that after calculating all of the eigenvectors, we can tell that this matrix is diagonalizable, right? Because it has 3 linearly independent eigenvectors. Next, we can sort of verify that theorem 1 actually does still work by checking that v1 and v2 are both orthogonal to v3. So we know that v1 dot v3 and v2 dot v3 are equal to 0. But notice v1 dot v2 is not equal to 0. So the two eigenvectors we calculated corresponding to lambda 1 equals 7 are not equal to 0. But that's okay, because we know that v1, v2 forms a basis for the eigenspace corresponding to lambda 1 equals 7. Right? And remember, what that means is that any linear combination of these two vectors must be a basis vector for lambda 1 equals 7. And that, in fact, every basis vector must be a linear combination, right? That's the definition of being a basis. So I've got a basis for this eigenspace. I know that every vector in this eigenspace corresponding to 7 must be orthogonal to v3. So all I need to do is find two mutually orthogonal eigenvectors for lambda 1 equals 7. But if given a basis, all I need to do is use the Gram-Schmidt process to find an orthogonal basis. From v1, v2. So that is, take the two linearly independent eigenvectors corresponding to 7, use Gram-Schmidt to find two orthogonal eigenvectors corresponding to 7. And this is, in general, how you will orthogonally diagonalize a matrix that doesn't have n distinct eigenvectors. So we will now use the Gram-Schmidt process to find. So we want two vectors z1, z2 that form an orthogonal basis for the eigenspace of lambda 1 equals 7. So remember what Gram-Schmidt tells me to do. Well, again, z1 is fairly straightforward. This is just equal to v1, which we know is equal to -1 to 0. z2 is equal to v2 minus v2 dot v1 over v1 dot v1 times v1. And so doing this, I got v1, which is 1, 0, 1, minus -1/2 was the dot product of v2 with v1, or sorry, oh, I did it a little differently than my work. Okay, let me just redo it then. v2 dot v1 should be equal to -1. v1 dot v1 should be equal to 5. And then we're going to multiply that by v2, or sorry, by v1. Yeah, what I did is I actually, in the solution, I hadn't yet cleared the fraction of v1, so that's what got me a little confused. And so this should still give us the correct answer, yes. And so z2 is equal to 4/5, 2/5, or z2 calculated this way is equal to 0, 4/5, 2/5, or 4/5, 2/5, 1. But remember, I can take any scalar multiple, so I'm actually going to let z2 equal the vector 4, 2, 5. And so z1 and z2 now, I'm going to replace the eigenvectors I previously had for lambda 1 equals 7. I guess I didn't need to erase v1, but -1, 2, 0. z2 is equal to 4, 2, 5. Notice now we have three eigenvectors, all of which are orthogonal, because by Gram-Schmidt, z1 and z2 are orthogonal. And you could quickly check that. -1 times 4 plus 2 times 2 is 0. Each of these two vectors you can still verify is orthogonal to v3. And so even though we began with fewer than 3 eigenvalues, using Gram-Schmidt, we can still find an orthogonal, or a set of orthogonal eigenvalues. And so now, if we want to orthogonally diagonalize A, we have one more thing to do. We want to let P be the matrix U1, U2, U3, where U1 is the normalized vector V1, U2 is the normalized vector V2, and U3 is the normalized vector UV3. And actually I have to make a small correction here. these should be Z1 and Z2, since we had to recalculate those using Gram-Schmidt. All right, so doing this, U1 should be equal to 1 over square root of the norm of z, which is root 5, times negative 1, 2, 0. U2 should be equal to 1 over 4 squared is 16 plus 2 squared is 20 plus 5 squared, so 1 over the square root of 45 times 4, 2, 5. And finally, U3 is equal to 1 over 2 squared is 4 plus 2 squared is 4 plus 1 is, so this should be 3 times negative 2, negative 1, 2. All right, so now this means if we let D be the matrix 7, 0, 0, 0, 7, 0, 0, 0, negative 2. We let P be the matrix, which is, by our calculations, an orthogonal matrix. Then A is equal to P times D times P inverse. And that is how you orthogonally diagonalize a matrix that does not have n distinct eigenvalues. So just going through that process again. You find the eigenvalues, or generally with these problems, the book will give them to you if the matrix is high enough dimension. Calculate all of the eigenvectors. And again, if the matrix is symmetric, you should have n linearly independent eigenvectors. For each eigenspace that has dimension greater than 2, in this case the eigenspace for 7 had dimension greater than 2, what you want to do is use the Gram-Schmidt process to find an orthogonal basis for that eigenspace. Once you have done that, normalize each of these eigenvectors you've found, and you have your similarity transformation. So I think what's interesting about this is that this doesn't have to be unique. Specifically, the way we applied the Gram-Schmidt process could have been done in any order. So this matrix P isn't actually the only matrix that could potentially be orthogonally diagonalizing A. So this gives way to theorem 3 in your book, which is called the spectral decomposition theorem for matrices, I think for symmetric matrices. And we'll quickly go over why that is, or why it is called the spectral theorem for symmetric matrices. So let A be an n by n symmetric matrix. Then A has the following 4 properties. 1, A has n real eigenvalues counting multiplicities. And so what this sentence means, it's a little misleading. It doesn't mean it has n distinct eigenvalues. What sentence 1 means is that A has what sentence 1 means is that the characteristic polynomial of A has n real roots. So it could have the same real eigenvalue with multiplicity n. So this isn't n distinct eigenvalues. This is the same, or this is just characteristic polynomial has n real roots, I think is the more accurate way of thinking about that. And as we'd mentioned, the dimension of the eigenspace for each eigenvalue lambda is equal to the multiplicity of lambda. This, of course, means that every symmetric multiplicity of lambda, that every symmetric matrix is diagonalizable. The eigenspaces are mutually orthogonal, and specifically the eigenspaces corresponding to distinct eigenvectors, or eigenvalues, I should say, are mutually orthogonal. We've already shown this one in theorem 1. For A is orthogonally diagonalizable. So this is sort of a theorem summarizing everything we've learned so far about symmetric matrices. I want to go over one more interesting thing. It's called the spectral decomposition of a matrix. We won't really touch on this too much in the course, but it's kind of an interesting application, and it's kind of a cool way to decompose a matrix, and well, specifically a symmetric matrix. So this is called a spectral decomposition. So let A be a symmetric matrix. Then if P is equal to this, where U1, UN are eigenvectors, of A, and P is an orthogonal matrix. I should say, actually, are eigenvectors of A corresponding to eigenvalues lambda 1 through lambda n, and P is orthogonal. This means that A is equal to P times D times P inverse, which, remember, since P is orthogonal, is equal to P times D times P transpose. And so this means that we can write this out like this. We're here, this is P, this is the diagonal matrix D with the corresponding eigenvectors on the diagonal, and P transpose, remember, is this matrix where we know the rows of P transpose are equal to the transposed columns of P. And so this means if we distribute these U1s through the diagonal matrix, we get lambda 1 U1 lambda n UN. And then multiplying this matrix times P transpose, we actually get that A is equal to this weird sum of what looks like it should be a vector but is actually a matrix. Which is called a spectral decomposition. And so this is equal to A. So this is called a spectral decomposition. So notice here, this is actually a matrix, right? Because if you think about multiplying a vertical vector times a horizontal vector in this way, let's say we had a vertical vector of length n times its transpose. Notice that doing the matrix multiplication dance, right, you'd get, well, so actually just to see that this is in fact an n by n matrix, this vector is an n by 1 matrix, this vector is a 1 by n matrix, right? So just off of this, you should get an n by n matrix, and basically what you're doing is matching up this entry with each of the individual entries in the rows and going across. And so what you're doing is, because A is symmetric, we can actually then just express it as this linear combination of sorts of its eigenvalues times its eigenvectors times their transposes. And so it sort of just provides this cool decomposition of a matrix when we know that matrix is symmetric. There's one more example of this in the worksheet. Finding a spectral decomposition is fairly straightforward. It just amounts to knowing the eigenvalues and having eigenvectors. So I'll leave that for you to look at if you want. I don't think there's actually any homework problems on this particular topic, so I just thought it was interesting, this kind of way of decomposing a matrix. So with that said, we are, that wraps up section 7.1. So next we'll move on to 7.2.